All right, so next up is Matt Ettus, who, Ettus Research is the diamond sponsor of the conference and is also sponsored every single student who got a student registration and is here. Yes. Thank you. All right, with that, I will hand it off to Matt.
Okay, so I'm going to give a brief update on where Ettus Research is and the exciting things we have done in the last year and where we're going over the next year or so. I will be sort of assuming that you guys have some familiarity with the products, but if there's something that's not clear, just throw up a hand. I don't want to leave out any information. As Ben said, we're sponsors. Really proud to have been sponsors since the very first one back in Philadelphia when 50 of us crowded into a very tiny classroom. And it's always, even then I was like amazed that, wow, there's 50 people coming to this thing. And this year we have 300, it looks like. So I'm always surprised every year and amazed and proud of the community that we've all built together. This I'm not really going to talk about much on this slide, except for I've always been excited to keep track of all the places that USRPs end up, and we have a map in the office with 124 countries. But now I can say thanks to the folks at Virginia Tech, the USRP has been to space, and that was always a personal goal of mine. So I'm really excited, and thanks to the VT guys, and they have a great poster in the poster session. So when you get a chance, go see it and talk to them. Is there anybody who hasn't heard of RFNOC, is not familiar with it? Good. So RFNOC is our system for making it much easier to program software radios on FPGAs, and it's pretty. It's not dependent on GNU Radio, but it's pretty well integrated with GNU Radio to make the whole process transparent for everyone and as easy as possible. So you don't need to be an FPGA expert. So over the past year, there's been a tremendous amount of development on RFNOC, and I just was going to give some of the highlights. So first, RFNOC is now, if you're using version 3.10, RFNOC is on all of the third-gen devices, so the E300 and the X300, and even if you don't realize you're using it, it's actually using RFNOC behind the scenes, and we have a compatibility layer so your old apps continue to work with that. So we're really all in on RFNOC, and it's going to be in all of our future devices, and we're really excited about it. A lot of the things we've been doing with RFNOC this year have concentrated on making it easier to use. So one in particular on that front is mod tool. So if you're familiar with GNU Radio mod tool, it is essentially a script that creates all the boilerplate and allows you to rapidly create modules just by inserting your code that's unique and not doing all the stuff that every block has. So we've now extended that to RFNOC, so all of that other stuff is created for you, all the build scripts and the XML and all that stuff, and you just can concentrate on your algorithm and the core of that. And this also enables the out-of-tree structure. So just like with GNU Radio blocks where you have OOT modules, we now have that capability for RFNOC as well, so you don't have to put your RFNOC stuff in our source code tree. You can keep it separate. We have helper modules on RFNOC to make it easy to do things like blocks with rate changing, blocks with bursty communications, including sort of fixed rate in, bursty out, for example, when you're doing synchronization to a waveform, and the reverse where bursty in and continuous out on the transmit side. So again, a theme of making it easier for you to develop blocks. Multi-port blocks. There's a lot of test bench improvements, and in particular, it now supports Xilinx XSIM. You no longer need the Mentor Graphics simulator. So this is a big one. The DDC and DUC used to be a required component, and it took up some amount of logic space, and if you weren't using it, especially on an E310 where it's not always necessary, it took up extra space that you could use productively elsewhere. So it has now been refactored out into its own block. And so what this allows you to do is remove it in those cases where you don't need it, gains you back a lot of space in the FPGA. Especially on the E310, this is important because it wasn't necessary and it's a relatively small FPGA. The other factor is that you can now have multiple DDCs and multiple DUCs. And this is helpful if you're trying to receive many signals off of a stream. Perhaps you're parsing a piece of spectrum into multiple sub-pieces of spectrum. You can use multiple DDCs to do that. So it helps when processing multiple signals in parallel. And of course, it's a lot easier to integrate with Vivado HLS now. And Vivado HLS, we'll talk about that a little bit more in a minute. So some great work by Sylvain. We have RFNOC, fosphor entirely accelerated in RFNOC, so you no longer need to use OpenCL. Which means you don't need a huge graphics card and to burn CPU power on your computer. It now can all run in the FPGA, and you just display it on your computer. And in addition, there's now also a web server for it, so you can serve it to any web browser. And in particular, it actually works quite well on smartphone web browsers. So you can walk around with your E310 in your pocket, running a little Wi-Fi access point. It's doing software radio and listening to a 56 megahertz chunk of spectrum. It does a real-time spectrum analyzer on it, and you can look at it on your phone as you go. And it, of course, doesn't have to be local either. It can be remote over quite some distance, because it's over the internet. So next, I want to talk about this really exciting challenge we're working on, and I guess challenges and contests are the theme of the day. We have the Bastille Challenge, we have this, and we also have the Spectrum Challenge, which we'll talk about in a little bit. So Vivado is, Xilinx and Ettus Research are teaming up to do this challenge with a $10,000 grand prize, and there will also be second and third prizes of USRPs and other equipment. And the idea is that we're looking for people to develop really interesting, really cool blocks or apps that use RFNOC and Vivado HLS. So Vivado HLS is a system that enables you to program either C, C++, or System C in your FPGA. So you can take what is normal a high-level language code that you would run in what you would call pure software and port it very easily to the FPGA. And so Vivado HLS is a really exciting tool, and we're starting to use a lot more of it internally at Ettus Research. And so the goal here is really to get people using these two great tools together and see what kind of exciting applications will come out of that. So to talk a little bit more about Vivado HLS, I'm just going to introduce John Shanton of Xilinx.
Hello, can you hear me? Yeah, so I'm a longtime radio developer, and I'm excited to see all the things that are happening in GNU Radio, but particularly one of the things that's sort of been missing is the ability for software radio folks to develop and to find the FPGAs tractable. The instruction level parallelism that was discussed this morning, that's precisely the problem that FPGAs solve in software-defined radios. However, most of you probably don't want to do programming in HDL languages and deal with clock domains and all that type of thing. And HLS goes a long way in solving this problem in that you do C development and you can get that to synthesized gates. The other piece that it really fixes, and this is really important to remember though, is that it's not just C as in a von Neumann kind of execution. What HLS does is it takes that C code, and particularly it does a really, really good job of unrolling loops and making them parallel. So pipelining is what it does really, really well. So in this challenge, I think that's one of the big big pieces of the challenge is how to leverage, C code and get it to pipeline and do really wonderful things that are challenging in von Neumann machines. So, thank you.
Thanks, John. So one of the exciting, we've been using, as I said, HLS a lot lately, and one of the great aspects of it is that you can program your algorithm, and then we wrap it, of course, into RFNOC, and it functions in the network, and all of the other things around it are taken care of. So you can just concentrate on that algorithm. And then HLS allows you to trade off area versus performance without having to change your code. And it's really, the things you can accomplish with it, rapidly produce different designs with different time and performance trade-offs is really impressive. So next, the third challenge of the day is by far the biggest. Some of you may have heard about the DARPA Spectrum Collaboration Challenge. We are really proud to be providing the user radios, the competitor nodes in that challenge. We were, of course, also part of the original Spectrum Challenge a few years ago, and it went really well. And this time around, DARPA has chosen to make this a grand challenge, one of the true grand challenges, if you remember the robotics challenges and the autonomous vehicles and that sort of stuff. And this is really exciting. We're really proud to be a part of that. And I definitely suggest right after lunch, Paul of DARPA, who's basically, the challenge is really his baby. He's going to be talking about it. So it'd be really interesting. And I really encourage everyone to think about participating. It's not a small undertaking, but it's really exciting. And to be honest, I wish I could participate in it, but because it would obviously be a conflict if we were involved. But it would it's going to be really exciting, and you still have time to sign up. I think it's a little bit less than 2 months before registrations close. But I really hope a whole bunch of people here will be participating. Okay, Balint showed a custom B200 mini enclosure, and I'm happy to announce that due to popular demand, we are now producing our own enclosures, and they'll be available. You'll be able to order them by the end of this week. So for those who don't know, the B200 mini is this credit card sized SDR that we produce that does USB 3.0 and 70 meg to 6 gig coverage. And you'll now have an enclosure for it, so you can put it in your pocket and step on it and things, and not have to worry about breaking it. It is sort of small enough that it's easy to lose track of. So anyway, we're excited about that. You can pick them up and hold them in our booth and see what they feel like. Okay, the next exciting new product for us is the TwinRX. This is an RF daughter board for the X300 series of SDRs, and the exciting thing about this one is first that you get 2 receivers in one daughter board, which allows you to get 4 receivers total in an X300, which would be 8 in one rack unit. So you can get 8 channels of 80 megahertz apiece in one rack unit. And the way we do that is, instead of using direct conversion like almost all of our other daughter boards, this board has super heterodyne receivers. And of course, at the end of a super heterodyne receiver, you don't have an I and Q A to D converter, you just have a single one. And so we're able to put 2 channels on the 2 converters and get twice the density. Also, super heterodyne does have some advantages for certain applications, and is quite popular in the spectrum monitoring and signals intelligence space. We've done a lot of work on this to make it ideal for things like direction finding, and in particular, you can do phased arrays and angle of arrival direction finding, which can be a very important application again in the spectrum monitoring space. So the specs, it covers 10 meg to 6 gig, 2 channels, of course, per board, 80 megahertz of bandwidth each. It's got full pre-selection filters, a high IP3, good dynamic range and noise figure, and it gives you a very dense, very high-performance system at a relatively low cost. And of course, it works with all UHD and all of our all of the software. So this is just a picture of 2 of them inside an X300, and you can see these cables coming across. These are actually the LO sharing between the boards. So in a setup like this, you have 4 receive chains. You also have 4 LO chains, but any receiver can share the other guy's LO. And so what this allows you to do is have, for example, all 4 receivers on their own LOs, and then when they see a signal of interest, they can switch over and share and do a direction finding operation on that. So this is a block diagram of the overall system. Of course, you've got both the X300 with the Kintex, the Kintex 7, 325, or 410T, and then the A to D converters and the daughter boards. And now, there's no transmit. In exchange for the 2 receivers, this is a receive-only application, transmitters. But in a receiving application, this is, this can be really powerful. So this is a block diagram. It's somewhat pixelated, so it's hard to read. But you can see it's a dual conversion superhet. So the first stage has the filters and the gain control and all that stuff. Then we have a mixer that mixes to an IF of either 1.25 or 2.35 gigahertz. And then that IF is further mixed down to a 150 megahertz IF. And then that 150 megahertz IF is sub-Nyquist sampled by the A to D converter. So the third and final conversion happens digitally in the A to D converter. So some people would call that a dual conversion, some would call it a triple. But there's 2 analog mixers and then the A to D converter. And then down here you can see the circuitry that allows for sharing of the local oscillators over the cables. So you can, each channel can either use its own LO, its buddy next to it on the board, or it can share from the other receivers on the other card in the box. So we've got filter banks that cover, nicely cover the bands with some overlap all the way out to 6 gigahertz. And so this protect against strong external signals and images and spurs and things like that. And just to give you an idea of it working, so this is assuming one X310 with 2 TwinRXs, each with 2 channels. And so you can have each of them on an independent frequency and be looking at 4 different signals. We'll call that mode 1. Mode 2 would be phase coherent LO sharing. So because you're sharing the LO, there's no mutual phase noise, so you get really good direction finding and phased array performance. So here they would all be sharing the LOs. And now you can switch very quickly between those. So if the 4 are on different channels and one guy sees a signal of interest, like I said before, you can instantly switch all of them over and figure out where that guy is. And then we have a third mode is Ping-Pong, where if you don't really need MIMO, you can be always acquiring, and one guy can be acquiring while the other guy is tuning. And so you get this Ping-Pong mode where you're basically always acquiring, and you can effectively very rapidly hop and scan very large areas of spectrum. So that would look like this. We would switch channels, and then the other channels are acquiring, and the first set are settling. So this device is really great for direction finding, and we actually have this application set up in our booth with a little array of 4 antennas, and you can move the little transmitter around and see how it points to the transmitter. So I'll just go over the block diagram here. We have the TwinRX setup. It's got 4 outputs because this is a dual TwinRX setup. If you had a single one, you just get the 2 outputs, of course. We have the phase correction block with the calibration for all the channels, because even though we share the LO, you still need to calibrate, calibrate your cables and the filters and everything. And so you get full phase alignment out here. Then we run this autocorrelate block, which is the first step of the music algorithm, and then which is the computationally intensive step of the music algorithm. Then the music algorithm itself, the final part that actually computes the direction vectors, and it outputs both to a vector sync to show the computation as well as a compass. And you can see that here. So it outputs, and you can sort of move the transmitter around and you see it follow. One thing I've been working on in my copious spare time is taking this autocorrelation block, which actually this code was developed by some folks at WPI that we were working with. But I've been converting the autocorrelate function to work in Vivado HLS, and it's been a really good experience. And so on Friday, during basically the hacker day, or the developer day, if anyone's interested, we can go over that and how it works, and we can show how we're able to accelerate the music algorithm. And we'll be able to go from, and really you should think about this, we've got 100 megasamples per second times 4 channels. So you're dealing with 400 megasamples per second. It's hard to run autocorrelations on that in any processor. And so when this is running in software, it's running at a lower rate. But once we can accelerate that in the FPGA, we can now do 80 megahertz, 100 megasample wide music algorithm, all accelerated in RFNOC. And additionally, the next step after that is to then do subbands, do a polyphase filter bank, and then run music algorithm independently on each subband. So you can find all of the signals in a band to spectrum and find out where they're coming from. So it's really exciting stuff, and I hope you'll take a look at it in our booth, and also stick around for Developer Day, and we'll see how it all works under the hood. So now the X300 with the TwinRX, very powerful device, but it doesn't fit in your pocket. It's not portable. So we also have a 4-channel receive version of the E310 coming. The regular E310 has a 2 transmit, 2 receive setup. This one will have 4 receives, no transmits. And this one is coming Q1 of 2017. We have prototypes here, and you can see them in the booth as well. But it'll give you the same capabilities as the X310 with the TwinRX, obviously with a significantly different dynamic range, right? The superhead, very high-end receiver in the TwinRX will have a much better dynamic range than this. But modulo that, this will be able to run the same RFNOC application to do beamforming, and you'll be able to port your application right over to this and have portable direction finding and all the same sorts of applications. Now, assuming you do that, maybe you don't want to walk around with it in your pocket. You want to put it on a telephone pole or on the side of a building so that you can have a stationary system that is finding signals and finding their direction. So we have this. This is the IP67 enclosure. If you're not familiar with that, it's like a waterproof, dustproof spec, environmental spec. So this is just recently completed all of the environmental testing specs, and it'll be for sale this month. So you can even submerge it up to some distance for half an hour or something like that. So it's intended to be put outside on telephone poles on the side of buildings, that sort of thing. It's rugged. It's got past vibration specs, all those sorts of things. And so this is really a deployable spectrum monitor device. You can also run it with the 2x2 version of the E300, and that and so then you can do 2-way communications again, deployed and outdoors. Some other cool things that have happened over the last year with USRPs. This is a massive MIMO setup at the University of Bristol in the UK. They have this has 64 X310s in it and 128 antennas, and they have set and reset and set again the world record for highest spectral density. So they have achieved 145.6 bits per second per hertz using massive MIMO. And the more you understand about Cons3, the more you understand how amazing that is. To be able to do that. And what they're able to do is 22 separate QAM 256 streams to 22 separate users simultaneously on the same frequency at the same time. And they're doing that with massive MIMO technology, which looks like it's going to be an important part of 5G communication systems. And we've also been working on large channel emulators. And so you can see this in our booth. This is a picture from the booth. This is showing a 16-way channel emulator and a phosphor display. And so you 16 channels, their effect on all 16 others, and this will scale up to much, much larger systems. And so what you have is that your 8 USRPs in this case. This is an octo clock. And then this is a device from National Instruments that has 4 very large FPGAs in it that serves as the computational backplane for all of this. And of course, this is all running RFNOC. So this really shows the advantage of the network transparency of RFNOC. We have the individual FPGAs on here do some processing, and then they pass to this big quad FPGA device to be able to do the full channel emulator, and then it sends the signals back to the individual USRPs, which then send them back to the radios. So that's in our booth. It'll scale to well beyond 16 antennas, but it's shipping more than that to a conference is impractical. Another device we've been working on is called Tritium. And Tritium itself is this gold outline, and then it's on this carrier board here. But this is a very stripped down E310 device, so it's all on one board. It's 2x2 MIMO, of course runs RFNOC, and uses the analog devices 9361 and the Xilinx Zinc chip, so it's great for UAVs and deeply embedded apps. And this version actually does have power amplifiers, so you can do significant transmitter power, and so it's ideal for UAVs, for video links and things like that. This is not released yet, but if you have an interest in this, talk to me, Manuel, or Tim sometime while we're here. Okay, and this is a block diagram, so you can see we've got the Zinc, and we've got RF front ends with the amplifiers and switching and stuff. This version in particular has half-watt amplifiers on each channel for the 900 meg, 2.4 gig, and 5 gig bands, but it's changeable to other bands as well. So in summary, RFNOC everywhere. We think this is a key technology for enabling software radio and doing interesting, very computationally intensive things without having to become an FPGA expert. We're going to be going to higher bandwidths, higher frequencies. If people are interested in millimeter waves, I'd love to talk to you, find out about your needs in that space. There's a lot of talk about that in 5G now. So let us know, what sort of other requirements you're looking at. Higher density, massive MIMO is a big thrust for us, and reduced swap and remote management of devices as well. So that we have that, for example, that E313 with this outdoor enclosure. The goal is you don't have to go out there and send a guy with a USB stick to fix it. It's all remotely managed, and that's really the goal with all of our devices, that you can make them more deployable. Because really, software radio, when I started, all this in 2003 or so, it was everything was on your desk, and if something went wrong, you can power cycle it. But now these are real serious applications in professional environments, in deployed environments, in hazardous environments, and so it's important that you don't have to go out there and power cycle. And so we've put a lot of effort into making these manageable and reliable. So in any case, thank you, and come visit us at the Ettus Research booth, and enjoy the rest of the conference. Are there any questions?
Would anybody does anybody have a question? In the meantime, also, Seth, can you come up and start getting set up? We have one.
Hey, Matt, I saw a slide about the N300 recently. Do you know when that's going to ship, or what the specs are going to be on that?
So yeah, that device that's a future device that we're working on. It's going to be sort of a mid-range between the the high end and the low-cost devices. We're looking at early to mid next year for that, but we don't have a formal announcement of anything on that.
Any other questions?
Okay, great. Well, thank you.
Nope. All right. Let's thank Matt.